Today's speaker is Professor Carlo Rovelli. Carlo did his PhD research at the University of Padova in Italy under the supervision of Professor Marco Toller. He graduated in 1986 with a thesis entitled, and here my Italian is a bit rusty, so you'll have to excuse me, but something along the lines of Sulla quantizzazione della teoria della gravità. I believe that the English title would read something like On the Quantization of the Theory of Gravity. Following his PhD, Carlo held a postdoctoral position at the University of Rome and at Yale University. And in 1990, Carlo joined the faculty of the University of Pittsburgh, where he worked until the year of 2000, when Carlo took up a professorship at Centre de Physique Théorique des Luminis in Marseille, France. He's also currently a distinguished visiting research chair at the Parameter Institute and a core member of the Rotman Institute of Philosophy at Western University, Canada. Professor Carlo Rovelli's work concerns unifying the two most fundamental theories we know of, general relativity and quantum mechanics. In the 1980s and the 1990s, Carlo, with colleagues, invented the loop theory of quantum gravity. Since then, Carlo has been investigating various aspects of how to quantize spacetime. On top of all of this, Carlo is a popular science writer. He has the rare ability to explain difficult physical topics to the general public without upsetting the physics community. His book, 7 Brief Lessons on Physics, has sold over 100 million copies all over the world. Finally, Carlo Rovelli is the inventor of the relational interpretation of quantum mechanics, which we are very much looking forward to hear more about today. So with these words, Carlo, thank you very much for joining us, and the virtual floor is yours.
Thank you very much, David. This was a very kind introduction. Yes, so let me share the screen. Here it is, advanced portion of screen share, and start. The title is exactly the topic that you mentioned, the relational quantum mechanics. Just as an introduction, I got to thinking about quantum mechanics precisely because I was doing quantum gravity. And in doing quantum gravity, the task, of course, is to sort of write a theory that can allow us to predict what happens when we cannot neglect either relativistic gravity or quantum. But it's not just an issue of writing equation, it's also an issue of finding the right conceptual structure for thinking about quantum space and quantum time. And in doing that, one is forced to think a lot about not only what is space and time, but exactly how to take quantum mechanics. And that's why I've got to be part of this conversation about how to think about quantum mechanics coming from quantum gravity. I mean, asking whether there's a perspective on quantum mechanics that it's useful, can be effective for thinking about quantum space and quantum time. So this, what I'm going to do today is give you a sense of what is relational quantum mechanics, which is an attempt to give a contribution to this, this conversation, which I think it's a useful one. It's not useless as sometimes it might look. On quantum theory, how to think about quantum theory. All right, so let me start by posing the problem. One of the many ways of posing the problems that quantum mechanics raises conceptually. One way is the following: there are many ways of looking at the theory, and I've listed here how many there are, 5. Perhaps the most common. One is just to use the theory to describe quantum systems as they are dealt with given a classical world in which we are. This is very common for whoever works in a laboratory with a small quantum system. Is very common among many practicing physicists. It's very common if you're a quantum chemist or a quantum biologist. It works very well, of course. It sort of leaves open the question, but the quantum world itself must be quantum. That's what 100 of successes of quantum theory suggest. Can we think quantum mechanics of the basic theory of everything, not just a big pieces of the world when everything else is quantum? A popular way of addressing the problem is many worlds, which, since I'm talking to Cambridge, I can say that one of the negative things of it is that it's particularly popular in Oxford, which is the idea that, as you know, when you measure spin up in a Stern-Gerlach, there is another copy of you that is, say, spin down somewhere else in reality. This is, I think, also a consistent way of thinking the theory that doesn't require assuming a classical world a priori. Another possibility is to assume that the theory is actually incomplete as it is, even if its predictions are what they are and are correct, and there are some hidden variables which is more than what is in the theory, in the usual formulation of the theory, and that make the theory more comprehensible conceptually. The best version we have is a Bohmian theory, which works spectacularly well, I would say, for a single non-relativistic particle, and then less and less well when you go to relativity, quantum field theory, and even quantum gravity. Another way is to give up sort of the, how would I say, the natural realism that most scientists entertain, and just think at quantum theory as a way for rational agents to compute what to expect next when they interact with the world without asking what happened in the world at all. This is a perspective of cubism. And finally, another radical, completely different possibility is to think that as it is, quantum mechanics is actually not coherent, conceptually coherent, and maybe it's just an approximation of something else where things are much more coherent. An example of that is all the ideas that quantum mechanics is wrong in the sense that it's a physical collapse, something really happening when the wave function collapses. It's a physical process that we have not yet learned how to describe physically. So these are a number of perspectives out there. And what I'm going to talk about is the question of whether it's possible to understand quantum theory, quantum phenomena without avoiding all of that. So without many words, without hidden variables, without necessarily thinking about rational agents betting about the future, and by taking the prediction of quantum mechanics as they are. So not trying to interpret the theory as an incoherent approximation of something else, and also not assuming that there should be a classical world not described by quantum mechanics to start with to make sense about quantum mechanics. So the question is, can we avoid all that? Is there another way? And the answer that I'm going to suggest is yes, and this is what relational quantum mechanics is about. And it's based on two ideas, which have their own part of radicality. I think quantum mechanics is strange and funny, of course, and whatever you do to try to understand it more clearly, there is always a cost, a conceptual cost that you pay somewhere. So, of course, relational quantum mechanics has its own conceptual cost. Each one of the previous of these different ways of looking quantum mechanics is sort of fiercely defended by somebody as the regional one, or sometimes even the correct one. Correct is a very loaded word. I'm not sure it makes sense here. And each one, it's strongly criticized by somebody else in the community. Because each one of these requires us to make some conceptual step, which is sort of painful for somebody. Let me put it this way. So the answer of relational quantum mechanics is yes, all this can be avoided at the price of making two steps. The first one is pretty simple and is common with many worlds and with other interpretation, namely take all systems as equivalent, including the quantum system you're observing, the apparatus yourself, the classical world, treat all system or universe on the same footing, even when in the application of quantum theory, you treat one of this quantum system and one of observer. So the observer itself is a quantum system with respect to another observer, so to say. And the second, which is the peculiar step, what characterizes relational quantum mechanics, and what I would argue, if one bites the bullet, allows to make sense of all the strangeness and the apparent incongruence of quantum mechanics, is to assume that when we're talking about physical facts or physical properties, we're not talking about intrinsic properties of a system. Spin is up because there's a system there that has spin up, but we're talking about interactions between this system and something else. Interaction in the sense of a collision, not in the sense of the weak interaction or the strong interaction. So ways in which the system affects some other system. And so the physical properties and the physical facts that a system process undergoes can be understood as relative not to the system itself, but the system and something else. This is the relational aspect of quantum mechanics. And now the claim of relational quantum mechanics is that if you take these two ideas, you have a way of thinking about quantum mechanics that avoids many walls, hidden variables, and so on and so forth. How does this work? To go into the idea, let me have just a few minutes historical introduction to the point, because I think it helps, even if it is just history.
Sorry, before you move on, I have two questions that have been asked here, if I may interrupt.
Sure.
So regarding these assumptions, under which of these would the Copenhagen interpretation lie?
The Copenhagen interpretation would break the first one, in the sense that you always assume that there is a classical system with respect to which things can be measured. If you take the Copenhagen interpretation in a sort of more democratic sense, and you think that, well, I could play Copenhagen interpretation by taking as observer anything, then you do relational quantum mechanics. Somehow above the interpretation mentioned before, the closest to relational quantum mechanics is the Copenhagen interpretation. What relational quantum mechanics add is sort of the idea that the Copenhagen interpretation makes sense whatever observer you choose as your Heisenberg or Bohr observer.
Okay, great. And I have a second question here. So I think the second point refers to the second of the two ideas. Is this, or how is this different from contextuality, or is this the same as contextuality?
It's contextuality. It's exactly a way of making contextuality as precise and clean as possible. That's I will go into it in detail.
Okay, great. Thank you.
It is contextuality. Yes. Okay. So I was, as I was saying, whoops, something moved here. As I was saying, there are two ways we can teach quantum mechanics typically. One common way of teaching quantum mechanics is that quantum mechanics is about a wave or a quantum state, more in general, psi. Quantum mechanics is about psi, right? Well, that's what we learn at school. That is governed by the Schrödinger equation. And then something happens, and somehow some probability comes in that the psi tell us what happens in some manner. There are even some radical way of thinking quantum mechanics that would like to say quantum mechanics is nothing else than a Hilbert space with a state moving in it and a Hamiltonian that tells how the state moves, and all the rest follows. And there are less radical versions of that. This way of thinking, of course, is rooted in one of the two acts of birth of quantum mechanics, which is Schrödinger 26 in his famous work on wave mechanics. But of course, quantum mechanics was born the year before, in 25, in Göttingen, in the paper by Werner Heisenberg and the series of papers that followed it immediately by Born, Jordan, and Heisenberg himself, and Dirac independently, who read the paper by Heisenberg, and then one should add Pauli, who actually computed the spectrum of the hydrogen atom before Schrödinger. And in this other way when quantum mechanics was born in this other way, there's no psi, there's no quantum state that evolves continuously in time, the thing is radically discrete. There are properties, A, that are realized at some specific times, T. And what the theory tells about is a probability of jumps from one property having a value of some time to the same property or another property having a value at a different time. And remarkably, the main equation is xp minus px is IH bar, in the sense that this equation alone, plus the classical equations, and in particular the function, the explicit functional dependence Hamiltonian on x and p and other variables on x and p, which are assumed to be the same as in the classical theory, are sufficient to define the theory. So the theory is defined by xp minus px is IH bar. And this way of viewing the theory, this quantum state plays no role or a minimal role, just a way of remembering, sort of keeping track of the last value of a variable that was realized, and making computation about the next one. Here is a way of presenting this this way. The mathematics, it's basically variables like in the classical theory. But these variables form a non-commutative algebra, especially in the work of Dirac. This is particularly clear, of course. So this is the main equations on which everything relies. So is the algebra of variables the essential thing, and not the state moving in a Hilbert space? These variables have values which are realized in observation. I will come back into that. That's exactly where contextuality comes in. And because and the key feature of the theory formulated in this way is discreteness, because the assumption, the idea here is that the possible values which are realized in observation are in the spectrum of the algebraic quantity that represent the variables, and from the algebra there are ways of computing the probability. I just put a paper here because it appeared on the archive today, and is a historical paper that I wrote with John Heilbronn, who is one of the major historians, on Max Born and on the matrix mechanics, the birth of quantum mechanics in Göttingen. So this is a possible way of thinking about quantum mechanics. So variables, probabilities, discreteness. This is, of course, one of the roots of the so-called Copenhagen interpretation, and a key aspect of it is that a quantum system doesn't have all its variable having a value at any moment, as you all know, and what has a value depend on the context. And here is a way Niels Bohr talks about contextuality in a way which is very precise in this phrase, which I'm going to read by Niels Bohr, because I think if one starts from that, the jump to relational quantum mechanics is particularly simple. This is one of the points in which, in my opinion, Niels Bohr captures something very crucial about what is it that we have understood about the world in understanding quantum mechanics. So Bohr said in classical physics, the interaction between an object and a measuring apparatus can be overlooked. So you can overlook the apparatus. In quantum physics, this interaction with the apparatus is inseparable is an inseparable part of the phenomenon. So the phenomenon is not about the system by itself, it's about the system and the apparatus. And therefore, says Bohr, the unambiguous description of a quantum phenomenon is required in principle to include the description of the relevant aspect of the experimental apparatus. Very simple, right? If a particle has a position, if it interacts with an apparatus to measure position, a particle has a momentum if it interacts with a particle that has a momentum. So the position of the particle is what happens when the particle, when the system, quantum system interact with certain apparatus. The momentum is what happens when it interact with a different apparatus. Now this is, it's correct, but it's correct somehow in a view of quantum mechanics. This is one of the 30s, when Bohr was writing these things, where quantum mechanics was in a lab, right? Experimental arrangement, apparatus. But 100 years later, given the spectacular success of quantum mechanics and things including cosmology, structure formation in the galaxies, what happened in the sun. There are no apparatus there, there are no experimental arrangement. I would say that the proper way of reformulating the same idea is the following. This is the key jump to relational quantum mechanics, to replace apparatus and experimental arrangement with whatever else is interacting with the quantum system. So let me rewrite more in the following language. And this is sort of the core hypothesis, the core credo, if you want, of relational quantum mechanics. Classical physics, the property of an object are determined irrespectively for the interaction between the systems, this object, and others. Quantum physics is the discovery that the interaction are inseparable aspects of these properties. So system having properties is not something that pertain to the system, but is something that describe how the system affects something else. And therefore, an ambiguous description of an object requires the inclusion of all the objects involved in the interactions in which the object manifests itself. So instead of observation, which is so anthropocentric, one can talk about just interaction between different physical systems, instead of observables, just relation between physical systems. So here is a key idea. Given we can think about the world, the system S, the system O, system P, they interact. The properties of the system S are things that come about when there is an interaction with something else, when S is affecting something else. And so when it's not, and it flows immediately from what I followed before, but it's radical, of course, it makes no sense to talk about properties of the system S. It has no meaning. Okay, because properties is what happened when the system affects something else. And when it does, a certain value, a certain variable, a certain value A at certain time, which is the time of the interaction. The interaction can always be described, the world can always be described as a set of discrete interactions. This is deeply Göttingen, Copenhagen, discreteness. Furthermore, because a property of S is manifested with respect, say, to O, we should remember that this is something that is a property of A with respect to O, and not, and that's a central part of the story, a property of S with respect to something else. So all properties are labeled with respect to the system that makes them manifest. And let me immediately jump to the sort of the key technicalities that allows this to work. In quantum mechanics, we compute probability amplitudes. What is the probability of A given B? What is the probability of fact A given B, or a certain variable having value A if another variable have a value B? Well, we should remember that these are properties of a variable A of the system S relative to O, given that there was a variable B relative to O. So this is meaning, but if we try to use quantum mechanics, we make a mistake if we try to use quantum mechanics by thinking that these probability amplitudes make sense when mixing properties relative to different systems. So this has no meaning. So that's
a quick interruption on this slide for you. So would one believe that there is some underlying real ontic states, or is there no underlying structure, only interactions and information transfer?
The second.
Okay, there we go. Clear answer.
Okay, so I'm gonna go to the end of what we mean by one believe, but let me go ahead at this level. So here's the relational interpretation. The systems, the world can be decomposed into system interact. This seems to be working very well for describing the world. There are variables. These variables mathematically form a structure which is an algebra. A quantum event fact in the world can be described by a variable taking a value, but this happens in interaction, and the value is relative to interacting system. And then the value that a variable can take, it's one in the spectrum, and the probabilities, there is a little machine for computing it, which I'm not going into, everybody knows it. And finally, the classical world it's not needed for talking about all the above consistently, but is what happens when there is enough decoherence for appropriate things to happen, and I'll say that in a moment what it is. So let me go to the core of the story and say why this work by illustrating perhaps the main puzzle of quantum theory, which is the Wigner friend situation, in which Wigner, here is the boy, it's looking at a situation in which the two systems was an atom and one is his friend, here is a cat. And the common Wigner story is that the friend, the cat, sort of measures the spin of the atom. The atom is a superposition spin up and spin down, and C spin up. Spin up is little a, okay? Now, no problem like that. That's what we do in the laboratory all the time. The problem is that if we believe quantum mechanics, Wigner can put all this in a box and measure a quantity which does not commute with this spin in this direction measured by his friend, and so would see something that he interprets as interference between the two branches, spin up and spin down. So with respect to the cat, the spin is up, but with respect to the friend, in some sense, neither, because if he expects spin up, he would make a mistake in computing that there's no interference between the two branches. If he projects the wave function, collapse the wave function, and kill the other branch, he makes the wrong calculation, okay? But that would be a mistake, because he would be using, I go back to this, using a probability with respect to the cat for computing something with respect to himself, and that would be a mistake. So Wigner from the outside correctly does his calculation with a state which include the two branches, if you want, the superposition of spin up and cat spin up and spin down and cat seeing spin down. All right. So this is the way the stranging of quantum mechanics is resolved into relational quantum mechanics, by saying that the spin up here is relative to the cat, not relative to the friend, not related to Wigner. So no surprise that for Wigner is irrelevant what happened inside. And more mathematically, the core problem of quantum mechanics can be expressed in this way. Probabilities, just in probabilities theory, satisfy this equation under suitable condition that you all know I'm not going to list, that the probability of C given A is the sum of a B, or the probability A given B, and the probability of B given C, where B are exhaustive, etc., etc. And now this, of course, is what fails naively in quantum mechanically, because probability of a square of amplitudes, okay, and the amplitude do have the property that the sum of the amplitude of C given A is the sum of the amplitude of C given B times B given A. But of course, now if you do the modulus square, you have this is a sum, so you have the sum of the square of the individual terms plus interference terms, okay? And so it seems to violate the something that is needed in quantum mechanics, in probability theory. Why is not the case? Because when this is violated, the typical case is the following, okay? This is the system, S1 is the system, S2 is the cat, S3 is the boy outside, S2 is friend, S3 is Wigner. A is something relative to S3, to Wigner, C is something relative to S3, but B is not something relative to S3. So it's not true. This equation needs not be true, because B are values not with respect to the same system as the system with respect to which C and A are values. Here is saying the same thing in other words. Let me skip this. So the tension between the unitary evolution and the wave function collapse in the sort of von Neumann formulation of the mystery of quantum mechanics, right? There are two kinds of evolutions, is resolved because values are relative to systems. So when a system computes, so the probability distribution of something that happens with respect to a given system is always given by the unitary evolution, okay? And it's always, and the collapse is always resolved with respect to a given system. So there's no conflict between the two cases. And of course, this is completely democratic. In that sense, relational quantum mechanics is Copenhagen made democratis, because no system is special in that. Of course, you don't have to go through all that. If you just fix a system and with respect to that, you do quantum mechanics, then you don't have these problems. Okay, like you do in cubism, or you do in sort of textbook quantum mechanics. Now, from this perspective, the wave function, and this is one of the questions that was asked a minute ago, should not be taken too seriously. The wave function is just a way to code the previous result. The wave function is always Everett relative wave function. In a sense, relational quantum mechanics is very Everettian, because it's Everettian without the global wave function. Okay, it's Everettian like in Everett paper, not like in the followers of Everett paper. Okay, the wave function is just a way. It's always a wave function of a system with respect to another system. So it doesn't describe a system. It describes what another system sort of knows about one system. So factor relative to physical system.
I have another question, or a few questions from the audience here. So one question is, could you comment on the role of the classical world in your interpretation theory in the framework of Caldera-Leggett diffusion?
I don't know what is Caldera-Leggett diffusion. What is it?
Okay, maybe if the person asking a question wants to specify.
Let me jump to the classical world. So maybe it's a general in the general. So this is a slide about the classical world.
It's like a quantum diffusion model, if that helps. It wasn't my question. I just
Okay, let me answer in general about the classical world. We have learned a lot about decoherence. Decoherence is a physical mechanism that happens when you interact with the system, but there's an environment. There are many variables in which information get dissipated. And if you do not have access to the environment, something very peculiar happens, which is that if a system gets entangled with environment, this is just a sort of super short account of decoherence. If a system, B is the state of a system, gets suitably entangled with environment, and if the state of the environment with which the system is entangled are sufficiently orthogonal to one another, okay, the many the information is it's lost there, and it's orthogonal. If the state here, the scalar product is small, then when you do not look at the environment, when you trace of the environment, you trace of this part here, you get a density matrix for the system, which is a superposition, a classical superposition, or the quantum superposition of those eigenstates here, plus a term which is as small as the is small when this orthogonality is sufficiently realized. And when it's so, the probability story that I said before works, because interference terms are suppressed. Okay, which means that you don't have to anymore to say with respect to which system C, B, and A are realized. So in the present of decoherence, you can delabel the facts and just consider them as absolute, which is exactly what we do in the world. Okay, this is a same story, if you want, that happens in many worlds. When there is enough decoherence, you can forget about the other branches because you don't see them anymore. And so it's very clear how, from this understanding of quantum mechanics, or if you want, this ontology of quantum mechanics in terms of relative facts, in a situation in which there is this physical phenomenon, which is decoherence, a classical world emerges. Classical world being one in which there is no interference, in which things have a value which is not relative to something else. So this is an answer to the question.
And I just have a quick other question on the last slide you had. So when you commented on what Everett said versus what Everett's followers believe, can you clarify a little bit more what you mean by that? So what did Everett say in his original?
Yes. So one of the key intuitions of average, which is completely absorbed in relational quantum mechanics, is when you are in the laboratory and you describe a system, you write a quantum state on your notebook. This quantum state, it's a relative state. This is a state of the system relative to you, okay? If you and the system are in a big box observed by somebody else, with somebody else, there is a bigger state of which the thing that you're writing is just a little piece, just one branch out of the larger one. But the key idea here is that states are not associated to a system, associated to system. And that's exactly what Everett insists. The relative state of system of Everett is system S and system O have a relative state with one another. Now, one way of working with this fantastic realization by Everett is to take this very seriously and say, good, so we're talking about relative states, we're talking about relative variables, because when there is branching, there is this possibility of variables having value, period. Okay, and that's what relational quantum mechanics does. Another way, different, is to say, okay, all this is immersed in a single super quantum state, and all these are branches in a big quantum state. Assign a heavy ontological weight to this quantum state and say this is what reality is. Okay, and this is the version of many world, which is this is many world, if you want. This is a personal version of many world, which is popular with Simon Sanders, Sean Carroll, and other, and to some extent David Wallace. So the people who are in love with many worlds. Relational quantum mechanics takes all the same mathematics, the same ideas, the same idea of relative states, but doesn't make the step of assigning a heavy ontology to this overall state. The other way around. I mean, since relative states are just essentially coding of what a system has learned about another system in the interaction, just interpret the state as that. Maybe I can I go ahead?
Yes, thanks.
Maybe since we are on this, let me comment more on this. So what is a wave function? What is a quantum state? And I would strongly argue against taking the quantum state too seriously. Now, let me make a little argument here. In general, when we learn something new, I don't know, relativity with respect to pre-relativistic physics, there are concepts which are a little bit different than before, but to understand what we mean, we connect to the previous theory. Mass, special relativistic mass is not the same as non-relativistic mass, but we take the limit, we say that mass is mass, we use the same name. So a good way in general to make sense of a quantity in a theory is to see what happened in the limit where we understand them. And of course, the wave function in the limit which understand is semi-classical limit is just the Hamilton function, okay? It's exponential of I over h bar, the Hamilton function in the semi-classical limit. And in fact, the Schrödinger equation is just the iconal, has as an iconal approximation the Hamilton Jacobi equation. Okay, so psi should have the same interpretation of the Hamilton Jacobi function, but now nobody would dream giving a Hamilton Jacobi function a direct ontological weight, right? We are describing a particle with an Hamilton Jacobi function, classical mechanics, not because we think that the particle is a Hamilton Jacobi function spread all over. Just things spread all over, just a way for us to computing where the particle is going to be. It's a technique for coding something about what we know about the particle and computing where it goes. So I think that's a good way of viewing the wave function, is a way of coding something we know about the state and predicting where it's going to be, but what is going to happen. But the thing the theory talks about, in the classical theory, it's the position of the particle. In the quantum theory, is the position of the quantum system with respect to a system that interacts with its position, or the momentum quantum system that interact with it. Now, one is tempted to take the wave function seriously because of picture like this right one, right? These are the orbitals of the in an atom. Okay, this is a picture of the wave function, but be careful, because one is tempted to take the caloric ontologically, because this is a picture of the caloric, right? This is a picture that tells me where heat is, but heat is not a thing. Heat is just a mathematical description of how particles move. So it's not a thing which is lighted here, and it's not a thing what is lighted here. So the fact that we have picture of something shouldn't take as a sufficient reason for taking a quantity ontologically. So the message here is, if you want to make sense of quantum theory, stop thinking of the wave function as the real thing. And I would say that the confusion, I'm wrapping toward the end here. The source of the confusion is exactly Schrödinger work, in my opinion. And let's follow Schrödinger, how he went into that. This is a text by Schrödinger. He says the inventor of wave mechanics, which is himself, of course, who else, indulged for some time in the fond hope that they had paved the way to return to a classical continuous description, okay, against the discreteness of the Copenhagen people, of Niels Bohr, the quantum jumps. But again, this is Schrödinger in the 50s. The hope was deceptive. Nature herself seemed to reject continuous description. The gaps, the jumps eliminated from the wave picture have withdrawn to the connection between the wave picture and the observational fact. The latter are not in one-to-one correspondence with the former. And this is Schrödinger again. It is better to regard a particle not a permanent entity, but an instantaneous event. That's Schrödinger. So, or more precisely, a sequence of instantaneous events when it affects something or other. And I want to just say a few words about discreteness, because discreteness, as soon as we start talking about how to think of quantum mechanics, we forget discreteness. Okay, when you think about many-world or Bohmian interpretation or most other interpretation, we take discreteness and we throw it away, which means we throw away H bar, we throw away the quantum phenomena. Discreteness is the core of quantum mechanics. Quantum mechanics was born with a wave finite discrete packets of energy, the photons, there's discrete levels in the atom, and so on and so forth. We know that there's discreteness all over in quantum mechanics. I think quantum mechanics is about discreteness, and I think it's completely general. Namely, in general, if you have a region of phase space, this is a harmonic oscillator, and you know from measurement that, say, the energy is between some value, some other value. In classical theory, you have an infinite number of possibilities, all the points in phase space. In quantum theory, you have a finite number of alternatives, which are a finite number of energies, which are E1 and E2. This is general. I mean, if you make a measurement which tells you that the system is a region of phase space, in quantum mechanics, this all to get more information about the system, you can only get a finite amount of more information. And let me jump to the argument about information, which I'm lost here, because, sorry. Here it is, which might be of interest to some of you. From the beginning, relational quantum mechanics strongly suggests to use an informational language for talking about quantum mechanics. Back in the 90s, when I started writing about quantum mechanics, I in the first paper in the middle of the 90s, I suggested that information is it's a right way of thinking, and we can write postulates in informational terms, which make the physical content of quantum mechanics more transparent. And then a huge, in various directions, mathematical, physical, philosophical, this evolves in various ways. Now, information here, in my opinion, it's not a fundamental notion that replaces the other notions in terms of which we describe the world, but is a useful concept in a theory where what is described is how systems interact with one another. And it's immediate to go from there for notion of information, because there is a definition of information, which is particularly simple. Information is all sorts of different meanings in different contexts, right? From very complicated, I have information about what my father did in his life, to very technical ones. And there's one notion of information which is already in Shannon, which is a notion of mutual information, which has nothing to do with semantic, nothing to do with anything high level, and it's just physical correlation. And it's the simplest one is a third or fourth page of Shannon celebrated booklet where he introduced information theory, and is the fact that two systems are correlated. They mean that the number of states of the two systems is less than the number of states of one times the number of states of the other. And information is justified, can be mutual information can be just defined as the something capturing this correlation, which of course means that if you look at one, you have information about the other, right? In usual terms. Now, using this notion of information, quantum mechanics in general can be largely captured by these two postulates, from which, with little addition, one can reconstruct Hilbert space, algebra observable, and things like that. The two being the amount of information, of relative information, I'll tell you in a moment what is relative information, about system is finite. And the second, that is always possible to gather new relevant information for every system. Now, the finiteness is exactly the discreteness I was telling you before. So if you have a system and you know that is finite, classically, it's phase space it's compact, it's finite. Then in classically, you can get an infinite amount of information about the system by knowing where it is with arbitrary precision. Quantum mechanics, the amount of the system that you can get is finite. For a spin 1/2 system, it's just one bit. Either spin is up or spin is down, okay? Now, relevant information is the information that is useful to predict the future. So if you measure spin up in one direction, and then you measure the spin in another direction, another direction, another direction, and you have the results, for predicting the future, only the last one is relevant. What happened before is erased by the last one. So the maximum amount of information of a spin 1/2 system is 1/2, okay? But yet, even if you have maximum information, you can measure something about another axis and measuring something new, of course, by making some of the previous information irrelevant. Now, it turns out that these two core ideas, which capture discreteness and probability, are sufficient to reconstruct, with few additions, the formulas of quantum mechanics. I don't go into the technicality. I just want to mention this. Here is some of the reconstruction based on these ideas. I think what is interesting here is that it's immediately, if variables take value with respect to systems, then what a system know about another system in the simple sense of mutual information. We measure one, we measure the other one, and we know something about the second, knowing the first. It's a core way of capturing the central structure of the theory. Okay, I close with a general information. I'm using a lot of time here, so I want to rapidly get to the end. In the following sense, is all this information, all discussion useful? I think yes. And the reason is because I do quantum gravity. Science is not just about numerical predictions of experiment. It's about devising concepts that help us making sense of the world. And as Feynman beautiful said famously, is that nature can be interpreted in different ways, but he says famously, every theoretical physics, when it's good, knows 6 or 7 different theoretical representations for exactly the same physics. And I would add, every theoretical physics who is any good knows about 6 or 7 different interpretations of quantum mechanics for exactly the same physics. We must all keep in our heads. I would push my students to think of the same system from a many-world perspective, from a Bohmian perspective, from a physical collapse perspective. Keep all of this in mind, because one of them may turn out to be fruitful in the future. And that's exactly the point of the story. The better clarity we have, this is why Bohmian, it's weak. it's fantastic for a particle, but then when you go ahead, it becomes less and less useful. So this is a sort of list of possible popular ways of viewing quantum mechanics, from Copenhagen to cubism, many world hidden variable, physical collapse. Relational quantum mechanics is sort of in the middle between a radical instrumentalism of some version of Copenhagen or cubism and realism in the sense of Einstein, adding pieces of reality that we don't see, which are not necessarily needed for having a better picture of what goes on, but what is going on between one value and the other and the other one. I think these are too extreme. The better we can navigate between the two. So use some measure of realism. Facts are real, but they're just relative, which doesn't mean they're subjective, of course, just relative in the sense in which velocity is relative. We can avoid the Scylla and the Charybdis of Scylla radical instrumentalism and the Charybdis of adding things which we haven't seen just because we want the world to be closer to what we knew about the world with classical theory. I use a lot of time. I wanted to say something about quantum gravity, but I think I don't have time anymore. I have just a few minutes. I'll just, I guess, flash a transparency. Let's see this one. In quantum gravity, why this is useful, quantum gravity? Because in relational quantum mechanics, the main idea is that you split the world in two, right? One is a system, one is a rest. And in quantum mechanics, you can do this split, this relational quantum split, in the same way we do the relational space-time split. In gravity, the position of something is always relative to something else. So in quantum gravity, you can take your process from, say, a measurement to another measurement in Copenhagen term, or from an interaction to another interaction in relational terms, to be a region of space-time. And the boundary to be where the quantum state is, where the variable takes value, and you have an amplitude associated to that, which you compute. So in loop quantum gravity, it's all about computing these amplitudes, given some interaction to another interaction. So there's no wave function, there's no need to go to asymptotic infinity. In that sense, at least in the way I do quantum gravity, relational quantum mechanics is a natural way to go. So I want to leave some time for more questions. I'll just close with the slogan: if you want to make sense of quantum theory, stop thinking of the wave function as a real thing, or in another word, listen to Heisenberg, not to Schrödinger. So thank you very much. I'll stop here. This is a list of papers, just in case you, oops, doesn't seem to be, just in case you might be interested in and I'll stop here.
All right, great. Thank you so much for this talk. And I have a bunch of questions here lined up for you. So we'll start right away with one related to the interpretations. So is there an experiment that would differentiate between the different interpretations of quantum mechanics, or do they have no predictive power?
Depending on what you mean, interpretation of quantum mechanics. If in the list I gave before, there is definitely an experiment that distinguishes the physical collapse interpretations from the others. About the others themselves, there is not. There is a lot of claims that there is experiment like that. Here is one, for instance, experimental rejection of observer independence of the quantum world. This is a experiment in which you simulate with a quantum system on an observer, and then you argue from the result that the fact with respect to this observer are only fact with respect to this observer and not fact with respect to other. I think this is very interesting because it shows aspect of quantum mechanics But any other interpretation could make sense of that. I think that a Bohmian could make sense of that. A many-world person could make sense of that. So the answer is no. But I said since the question has an implicit point, which is maybe that makes the discussion useless. So I'm answering another question here. I would say, look, is there an experiment that shows that the Earth is not the center of the world, of the universe? The answer is no. There's absolutely no experiment that can show that the Earth is not the center of the universe, because it's not an experimental question. It's a conceptual question. The point is that if you conceptualize astronomy by giving up the idea that the Earth is the center of the universe, everything works much better. No doubt, everything works much better. If you do like Tycho Brahe and keep the Earth at the center, you make things more complicated. You don't have the natural concepts for going ahead. Science is not just about prediction of numbers. Science is about finding a conceptual way of thinking the world, which is useful for us to go ahead and organize our thinking better. So that's, I think, what the discussion about interpretation of quantum mechanics is about.
All right, great. Thank you very much. So I've got another question from the chat here. Out of curiosity, what do you think about closed time-like curves in general relativity? Do you like any of the suggestions of how to reconcile closed curves with quantum theory?
I was born as a relativist, and I never found closed time-like curves dangerous or to be rejected in any sense. I think that the so-called paradoxes, like you go in a closed time-like curves and you kill your grandfather, are just confused fables, because you cannot take a solution of a set of equations and then pretend to walk over them and modify things at will. That's not the way this physics world. So I don't think that closed time-like curves are wrong, are impossible, or are contradictory at all. I think what is contradictory is the assumption that we can freely do what we want along a closed time-like curve. Obviously, we do not. Mm-hmm. The role that this is playing in quantum mechanics, it's a bit confused in the current discussion. I think there is a lot of work on non-standard causal structures in quantum mechanics. I think is interesting work. But I don't think is yet very clear conceptually, because it's based on assumptions which are not grounded in a physical theory and are grounded to some vague intuitions that in quantum gravity might be right or wrong. I think the best thing to do is to write a quantum theory of gravity to see what happened.
Okay. Well, maybe we can expect one of those at some point. So I have another question here. Where are we now in terms of quantum gravity? What are you most excited about in the field at this point in time?
Well, something is wrong in my. I wanted to put the. Sorry for this. I wanted to put the papers here. Here are my 2 books on quantum gravity. I think that we are in a much better situation than what is usually advertised. I think that there are tentative theories out there. One is string theory, in spite of its recent failures, and one is loop quantum gravity, and there may be others. I don't want to go to a list, because at some point I stop and somebody else get offended. So there are theories out there, and the reason there are many theories is because we have little experiments, and so the interesting work, in my opinion, is trying hard to connect to observations. But it's also true, and this is rarely said, that we have had a lot of relevant empirical information recently. For instance, the observation of the merging of the neutron stars ruled out a large number of alternatives to GR that seemed promising as quantum theory, that predicted that light and gravity have different speed in the waves. That's one. A lot of tentative theories of quantum gravity that predicted breaking Lorentz invariance at the Planck's scale is easier to do a quantum theory of gravity if you don't want to preserve Lorentz invariance, have been ruled out empirically, experimentally by astrophysical observations that show that Lorentz invariants seem to be still at energy at the Planck scale. We do have observation energy at the Planck scale astrophysically, and most importantly, supersymmetry. I mean, supersymmetry has been a huge hit against a part of the research toward quantum gravity, because of course, if you are in the world of supersymmetry strings and so on, you expected, the people did expect low energy supersymmetry on the basis of argument of naturalness and else, and people expected that dark matter could be a neutralino, the sort of lighter supersymmetric particle, stable particle, and nature has just said no. And of course, this doesn't rule out string theory, but exactly for the same reason, finding supersymmetry would have increased our confidence in that direction of research. Not finding supersymmetry has decreased our confidence in those, just by Bayesian confirmation theory. So nowadays, string theory looks much less promising as a theory, because what it naturally predicted is not there. The other thing that it naturally predicted is negative cosmological constant, and to everybody's surprise, the cosmological constant has been measured by the astronomers again, and is positive. There have been claims. I heard people, "Oh, it's a disaster. I mean, it's a crisis of theoretical physics not finding supersymmetry." I remember what's his name, Tong, giving a royal the lecture in London, the Royal Academy, and say, "Oh, it's a crisis of physics." It's not a crisis of physics. It's a crisis of his way of looking for development. I mean, for my way, it's a triumph. I mean, we've been saying supersymmetry is not convincing for years and years. Many people, not just me. I mean, there's an entire community. So I think that quantum gravity, it's in the moment in which we have theories. They're not complete. They have open holes. There are things to be not clear. And we need to struggle hard to see if there is something that connects to observation. What excites me right now, that was the second part of the question, is the study of what happened at the end of a black hole evaporation, because that's a quantum gravitational phenomenon, can be studied. I am working on a model in which there is a quantum tunneling to a white hole. So a black hole evaporates and becomes a small white hole, which is stabilized by quantum gravity, is a remnant living long time. The hopes of connecting this with dark matter, the hopes of connecting it with other astrophysical observation, if something like that works, we'll have pieces of empirical support for ideas toward quantum gravity. I'm optimistic, I'm not pessimistic.
All right, great. Well, thank you very much for this comment. So I have a few more questions still. One question is, can you comment on the connections with, or your opinions of, ADS-CFT?
Yes. Yes, and I can make two comments. ADS-CFT is an interesting theoretical fact that was observed between two theories, as everybody knows, by Juan Maldacena some time ago, and has excited many people. It's an hypothesis. It's an hypothesis of how the world could work. I would say it's an interesting hypothesis to explore. Somebody should explore it. But unfortunately, in my opinion, in a large part of the community has evolved into a belief. And when an hypothesis becomes a belief, we are closing our eyes and tying our hands and be ready to say whatever nonsense to hold the belief, right? And so to accept any sort of funny consequences on the basis of that belief, instead of taking the funny consequences as evidence that the belief is wrong. Okay, everybody who believes a dogma, it's ready to climb mirrors to hold the dogma true. And I'm afraid that this is what is happening with ADF-CFT. The case in which this is stronger, it's a so-called black hole information puzzle, which is not the question of what happens at the end of the evaporation, which is just a quantum gravity question. You have a quantum theory of gravity to see what happens, maybe information inside escape. Is the question of what happened before, when the black hole, technically it's called page time, becomes small, so that the Becker-Hawking entropy suggests that there are not enough states for purifying the Hawking radiation, and therefore something magic should happen. And people consider this a big mystery, but it's not a mystery. It's just an assumption that something like the FCFT works, namely that the internal state of the black holes are accounted for by whatever happens at the boundary outside the exterior. If you don't believe ADF-CFT, if you don't think it is a dogma, there's nothing wrong in thinking that the black hole shrinks, its thermodynamical entropy goes down, but the von Neumann entropy of the entanglement between inside and outside can stay up, because black hole is not ergodic. And for a non-ergodic system, von Neumann entropy can be higher than the thermodynamical system, because you only interact with a subset of systems. So the thermodynamic subset of variables of the system. So the thermodynamic system goes down, the black hole shrinks, but the von Neumann entropy is up. And then whatever happened next, the information is still there. And for instance, as I was saying before, it's a white hole, and slowly it comes out from a long remnant. So this is a typical case in which a nice idea becomes a dogma, and then people convince themselves that there's incredible mystery which follow from the dogma, right? If you allow me, can I be a little bit provocative? In Catholicism, there are two mysteries during the Mass. One is that the bread and wine become the real flesh and blood of Jesus. Then there's a second mystery, that the blood and flesh of Jesus look like bread and wine. I don't want to make fun of at all of religious people for whom I have immense result, but here clearly there is a dogma kind of jumping on itself. And I think that what's happening with black hole information paradox is similar. People fall in the trap of forgetting that that was an hypothesis and taking it as a certainty, and therefore getting confused when from that certainty one derived nonsense.
All right, well, good. We'll see if you've offended ADS-CFT people.
Okay.
All right, I have another question from the Q&A here. If you still have time, obviously.
Sure.
Okay, so the question is, if system A, this is more related to the relational quantum mechanics. So if system A influences system B, which in turn influences system C, and so on, where do we pragmatically place a boundary when describing the system? Or do we need to have this boundary to avoid a radical conclusion that no particle system can be isolated from the rest of the universe? Now, this is in reference to how relational quantum mechanics describes properties of objects and forbids them from existing in isolation.
Yes. It's a constellation of questions. First of all, if you buy relational quantum mechanics, that's how you have to describe the system. That's the only thing you can do. Namely, you can describe the system S, how it affects O. So let me use a figurative language. You can describe S from the perspective of O, what O knows about S, okay? You can also describe O how it affects P, so O with respect to P, and so on, as you wish. okay, but you cannot jump out from this. You cannot describe the full thing consistently, how it appears to something else which it doesn't exist. The boundaries in which you split the systems are arbitrary, and that's we know it very well from quantum mechanics, right? One of the beautiful aspects of the quantum mechanic formulas, since when we studied at the beginning, is that we put a Heisenberg cut-as this is a separation between the quantum system and the classical world, and we know we can move it out as we wish, and our final prediction don't change. So this is the same in relational quantum mechanics. Of course, you can move this boundary as you want, and the thing always works. And there are a lot of technical little games of showing that this is the case, this is never contradiction, and so on and so forth. So if one goes to this logic, the world can only be described from within. A part of the world can be described with respect to another part of the world, namely the fact pertaining to S always related to something else, so can be described as relative to something else. If you want to describe everything from the outside, there is no meaning into that. So boundaries between systems are needed. Where you put this boundary is arbitrary.
All right, and we have one last question here by Campbell. If you can start your video, and so this is a math student.
Oh, hello. I think I've got.
Hi, Campbell.
Hi. So I just had a quick question related to some talks in a different seminar series that some of us have been attending. So sorry for if there are those that haven't been attending, but so there were some talks about quantum reference frames by Filomena Giacomini and others, which seems to relate quite a lot to relational quantum mechanics. But I'm wondering if that perspective is sort of subsumed into relational quantum mechanics or the other way around, or if they're quite distinct ways of looking at quantum mechanics. So this is the idea that you can sort of go into the reference frame of a particle in superposition, and the rest of the world sort of may look entangled or other things like this. If you've come across this.
Yeah, I know what you're talking about, and it's a very good question, and it is a question that has raised a lot of debates in the community, and in particular in the KISS community, quantum information and quantum gravity, quantum information structure of space and time. The answer is less exciting than what you might hope. In the following sense, the spirit is very much the same. Okay, somehow the underlying ideology is the same. We describe system from a perspective. What happened if we change perspective? Okay, so at the beginning of the work of Flaminia and her collaborators and the others, there was quite an attempt to translate, to see whether same thing is being said in different languages. I think that the discussion has clarified that the similarity is only in the ideology and not in the actual what is going on, because in the quantum reference frame, especially in its original version, when you change reference frame, you're not changing observer in the sense of the Heisenberg cut. Is not that one thing which is your Copenhagen observer become quantum. Not at all. Okay. If you want to put all the dot on the I, what is really going on is that, say you have three particles down there, you're describing the position of two with respect to one, and then giving the same geometry by describing the position of two different with respect to one. So A, B with respect to C, and then you change, you say A, C with respect to B. But the measurements that you're doing, you're always outside and you're always the same observer. You're always Wigner from the outside. There's no Wigner friend inside. So the measurement are always made from the outside. And what is changing is that you have a sort of an invariant quantity, which are in that specific case, the invariant the invariant part of the three distances up to, so the three position up to global movement. So you have three variables of which, let's say in one dimension, three variables of which only two are independent. So it's just a change of variables in the same phase space, so to say. So from the abstract point of view, you just have a system with a redundancy, and you can just change the variables. And then, of course, there's a quantum mechanical story. If you use variables a function of the previous one, things changes accordingly, and in particular the dynamics change in a funny way, which Flamini has worked out. So it's not the same thing. Having said so, I think that the idea it's very good that we should keep in mind that very often what we're describing are relative variables, because it's back to the same idea, right? When we do physics, very often we think we're talking about one object, but really we're talking about an object seen from another, from the perspective of something else. So in that case, it's just a change of variable. In the quantum case, is a change of observable in the sense of the Wigner friend change of observable. They're different, but it's the same general idea, which I think is crucial and I think is important to digest, especially if one wants to go toward quantum gravity, where the two things get mixed up. You have to take into account both, in a sense. Precisely because in general relativity, because of general covariance, the only localization you can have is relative. So you can choose whatever you want as your reference with respect to which the other things are located, but you have to know how to change these variables, and you have to know how to change both in the quantum theory as a change of variable, but also to remember that this underpins the quantum separation between the system and the observer, the Copenhagen observer, or the relational other system with respect to things they are. So my answer is no, if I want to be technically precise. Yes, because that's the general thing we have to learn, how to describe things in relation to one another rather than by themselves. Hope I didn't mix up this too much. This was clear.
No, that's very clear. Thank you very much.
All right, great. So I think that's it for all the questions we had, unless David and Crispin, you have extra.
I think this is all I've seen. Yeah.
Yeah, me too. So, well, thanks for everybody who stayed the 20 minutes extra. And Carlo, thank you so much for giving this talk. I think it's a really great way to close this term's seminar series.